Okay, so for the second part of chapter 2, we start talking about those atomic mass numbers from the periodic table, so the mass of the atom. And in the future, I'll call those molar masses, if you remember that terminology from intro chem, or molecular weight or molar weight. But we're only looking at atoms in this chapter, so that's why it's an atomic mass. That also works. So why are they not perfect whole numbers? Well, we talked about the isotopes. And if I use copper as an example here, right, copper has two naturally occurring isotopes, copper 63 and copper 65. And what happens is you can take a sample of copper and you can separate the atoms by different mass. So the copper 63 is lighter and the copper 65 is heavier, and those atoms can be separated by that mass difference. And they can figure out then what's called the percent abundance. So the copper 63 is 69% of the copper sample. The copper 65 is about 31% of the sample. And we know the atomic mass of each of those isotopes pretty specifically. So when we go to find the weighted average of those two isotopes, you take the atomic mass of the isotope times the percent in a decimal form. So 69.17% converts to 0.6917. And you add that to the atomic mass of the second isotope times the percent abundance for that isotope. When you add those two together, you get the weighted average. And if you look at the periodic table, that's what you'll see for copper, 63.54. So that's where we get those atomic mass values on the periodic table. I always use the molar mass or the atomic mass from the periodic table to 2 decimal places. I feel like that's good enough. So when we look at copper 63.55, right, because the 5 would round up. So that's what I use for my atomic mass for copper. Now the atomic mass, right, I had mentioned this a little bit ago. I also refer to that as the molar mass. And I think that's easier because then we don't have to worry about is it an atomic mass because it's just an atom? Is it a molecular mass because we're looking at a covalent compound? Is it a formula mass because we're looking at an ionic compound? Molar mass applies to everything. And the other reason why I like it is the mass of a mole. If you think about copper, right, and you have this 63.55. If it's a mass, the unit should be grams. But 63.55 grams, you can see that, right? That is a tangible quantity, but you can't see an atom of copper. So that mass represents a mole of copper. And the mole is a chemistry unit. It's only used in chemistry. And we like it because instead of counting every individual atom or molecule in a reaction, we can just use this substitution of a mole. And a mole represents 6.022 times 10 to the 23rd particles. In this case, because copper is an element, we're looking at atoms of copper. All right, so some conversion factors to remember, right? Your atomic mass represents a mole of that element, and that means it represents 6.022 times 10 to the 23rd atoms of that element. All right, so another example I gave here was carbon. So a mole of carbon is 6.022 times 10 to the 23rd. A mole always represents that same number. That's called Avogadro's number. And the mass of carbon would be 12.01 grams. Why is it so much less if it's the same number of atoms? That goes back to the atomic structure, right? Carbon has less protons, less neutrons, so it's not going to be as heavy. If we do look at a compound, this will be more so in the next chapter, we'll look more at compounds. But carbon dioxide, again, a mole represents 6.022 times 10 to the 23rd. But what's different now is the particle type is molecule, not atom, because we have a compound. And the mass of that, we find that by taking a carbon and 2 oxygens from the periodic table, because that's the formula for CO2. And that is our molar mass for carbon dioxide, 44.01 grams. So some examples with these conversion steps, it says, you may have heard this, that eventually they'll stop making pennies because the value of the copper will be more than 1 cent. So copper pennies are actually, they have a zinc disc inside, and it's just a coating of copper. So due to the rising value or cost of copper, a penny is now only 2.5% copper. The rest is that zinc disc on the inside. Knowing the mass of a penny is 2.500 grams, what would be the mass of copper in that penny, and how many atoms would be in that penny? So first thing is, we have the mass of the penny, 2.500 grams. And then if we know that the amount of copper there is only 2.5%, you have a choice. You can convert that to a decimal form, or you can say, okay, it's 2.5, and that is parts per 100. So 2.5 parts out of 100. The 2.5 is the mass of copper versus the 100 grams for the penny. All right, so we're going to convert grams of penny to grams of copper. So I'm going to take that 2.500 times 2.5 and then divide that by 100. And what I get here is 0.0625 grams would be copper. All right, now I'm not going to worry about sig figs just yet. Well, we're going to keep going because I'm just multiplying in the next step as well, and then we'll round to sig figs at the end. The next part of this was how many atoms would be in that. All right, so I'm going to take my 0.0625 grams of copper, and what I know is that 63.55 grams of copper is a mole of copper. And in that mole, there are 6.022 times 10 to the 23rd atoms of copper. So I'm going to take my 0.0625, divide that by 63.55, and then multiply by 6.022 times 10 to the 23rd. And here I'm going to look at my sig figs. The mass had 4 sig figs, but my percentage here only had 2 significant figures. So I'm going to round my answer to 2 sig figs. So 5.9 times 10 to the 20 atoms of copper. So still a lot of atoms in that penny. All right, then the last question here, looking at molecules. And again, there will be more of this in chapter 3. It says we have a 1 liter bottle of pure water, density is given, and we want to know how many water molecules would be in that sample. So I'm going to go ahead and put a little note here. Let's use 3 significant figures. Otherwise, the 1 liter, it just looks like 1 sig fig, but we're going to go ahead and, I would put a note here, do 3 sig figs. So we have 1 liter. A liter is the same as 1,000 milliliters. Remember, you can write it that way, or like we talked about in the chapter 1, you could write it as 1 milliliter is 10 to the negative 3 liters. All right, up to you how you want to do it. And then using my density, 0.998 grams would be the mass of each milliliter in that bottle. And then to get from grams to particles, what I need here is the molar mass of the water. And hydrogen is 1.01, but I need 2 of those for H2O. And then 16 for the oxygen. So if I add that, I get 18.02 grams. That would be the mass of 1 mole. And if I want to just show that in 2 separate steps, I certainly can. So there's my mole. And then 1 mole of water would be, again, Avogadro's number, 6.022 times 10 to the 23rd. Now, again, kind of noting this. Before, up above, we were looking at copper, which was just an element, so we had atoms, but in this case we've got water, which is a compound, so we have molecules instead. That's the distinction. All right, so I've got 1,000 milliliters. I multiply that by 0.998, so I have 998 grams of water. Divide it by 18.02 to figure out how many moles I have, and then multiply it by Avogadro's number to figure out how many total particles I have. All right, so I'm going to scoot that over. 3 sig figs, we get 3.34 times 10 to the 25 molecules of H2O. So that would be how many molecules of water in a 1 liter bottle. All right, so that completes the notes for chapter 2. So then I'll also be posting more videos about chapter 3 coming up.